So, hi everyone, can people hear me?
Yeah.
Okay, great. Just see if anyone else joins and yeah, we'll start in a minute or two. Can people see the screen? Okay. Cool. Okay, we'll start at 10 past and finish at 10 past. So yeah, we'll just start in 1 minute. Can we get access to the slides? I'll just ask about that actually.
Hey guys, regarding the slides, we don't actually give access to them, but all of these videos are recorded and uploaded to our YouTube. So to access them, please go to StudyMind on YouTube and you'll find them there.
Okay, so yeah, we can give the links at the end. So it should be on StudyMind YouTube channel. We'll get started shortly. So today we'll just be going over chemical equilibria and the Chatelier's principle. That's going to be regarding equilibrium reaction. Okay, so let's get started. So the main things we'll be looking at are reversible reactions and applying the Chatelier's principle, and a bit about the Haber process as well. Okay, so what is a reversible reaction? The reversible reactions are chemical reactions that can occur in both directions. So the forward reaction would be the reactant forming the product, and the backward reaction will be the products forming the reactants. And you'll generally see like a symbol that looks like this. You can see that there's an arrow going to the right and there's an arrow going to the left. An example of this is something called the Haber process that I think some of you might remember from GCSEs as well. So that's where you have nitrogen, hydrogen, and then you make ammonia. And this is a reversible reaction. This means that the nitrogen and the hydrogen can react to give ammonia, and the opposite reaction. So the ammonia can break down into nitrogen and hydrogen. So that's a backward reaction. What did we cover last week? I actually didn't do the one last week, so I'm not quite sure what we covered last week. But I can.
Hey guys, Shintaro didn't cover the last week's session, so that was with Hamza. If you'd like to find any previous sessions, please go to our YouTube channel. We've got all of the revision classes actually uploaded over there, so you'll be able to find the topics, etc. And I've actually put in the group chat the chat over here what the topics, what the YouTube channel is. So please go visit there, and you'll be able to find last week's recordings for biology and chemistry.
Yeah, great. Okay. So yeah, just to cover everything really quickly again, we have the forward reaction. That's the arrow going from left to right. And we got the backward reaction going from right to left. And this just means that you can go both ways. This shows reversibility. So now we can have something called a dynamic equilibrium. This occurs in reversible reactions. So basically what's happening is that you have the forward reaction going from left to right, occurring at the same time as the same rate and the same time as the backward reaction. So here, this is a really simplified diagram of a dynamic equilibrium. So here on the left, we've got A, which is the reactant. And then this reacts to give the products, which is B on the right side. But then we can also have the backward reaction where B goes back to A. And it's this forward reaction that's going at the same rate at the backward reaction, and we call that dynamic equilibrium. And we call it an equilibrium because the rate of the forward reaction is the same as a backward reaction. That means that the concentration of A and B, they remain constant. So it's still reacting, but the net change is 0. And that's why we call it equilibrium. So here's just an example of how a system could end up in equilibrium. So let's say you started a reaction by preparing a lot of the reactants, so A, and it reacts to form maybe one molecule of B. So this is still at the early stages where you just have the reactants. You have a lot of A being converted to B. But eventually, as more reactants react and produce B, you get more of the backward reaction where B is turned into A. So you can see here, A is converted to B and B is converted back to A. And then there could be a dynamic equilibrium where, it will remain at these 4 molecules of A and how many is there? 6 molecules of B, and it would just remain like that. The forward reaction is still going on and the backward reaction is still going on, but because they're at the same rate, the concentration of both the reactants and the products remain the same. And this would usually be in a closed system. That means that nothing can be added or removed from the system. And it's a bit of a nitty-gritty kind of thing, but you can kind of have energy going in and out. In an open system, you wouldn't really get a dynamic equilibrium because what would happen is that you could start with A being converted to B, but then B is lost. So then you don't get that backward reaction anymore. So a big high yield topic that always comes up in exams for reversible reactions is Le Chatelier's principle. So we discussed how you could have equilibrium. So in this example, we had 4 of A and 6 of B. Why couldn't it be 6 of A and 4 of B, right? So that's basically about where the equilibrium is. Is there more products or is there more reactants in the equilibrium? And the way we determine that is using something called the Chatelier's principle. This basically says that there are several factors. The ones you need to know are temperature, pressure, and concentration. And when you change these factors, the position of equilibrium changes. So for example, I might have a reaction where when I raise the temperature, the equilibrium will be at a point where there are more reactants rather than the products. I might have another reaction where higher the pressure, I get more products and less reactants. And Le Chatelier's principle helps predict how the equilibrium will change when temperature and pressure and concentration are changed. And it's actually quite intuitive. So let's go through each one. So we'll start with, okay, let's just go over the general rules. So more reactants will be produced if the position of equilibrium moves to the left. So this is just terminology. So what does it mean when equilibrium moves to the left? If you look at the equation, right? On the left side of the equation, we have the reactants. And on the right side of the equation, we have the products. So when we say the equilibrium moves to the left, it just means that at equilibrium, there are more products. Well, it will shift so that you're making more reactants and less of the products. Vice versa, when we say the equilibrium moves to the right, it means that we are producing more products and less of the reactants. So factors affecting position of equilibrium. So well, I'm gonna kind of just say it already, but the first 3, these are factors, but technically the catalyst, it's a bit of a tricky one. It's a common trick question where they'll ask you how catalyst affects the position of equilibrium, and the answer is that it doesn't affect the position of equilibrium. So the factors that you need to know are actually concentration, pressure, and temperature. And catalyst, it's always a trick question. It doesn't affect the position of equilibrium. So let's go through concentration, pressure, and temperature. I'll just read the chat a bit. Do we learn reversible reactions in year 12 or year 13? I think someone's answered that. I think it also depends on your school as well. I guess AS syllabus might have reversible reactions. I think it does, but I'm gonna have to double check that later for you. But we'll go through the catalyst at the end. So we'll just go in order. So good question there. So let's go through concentration first. So remember that the square bracket kind of shows the concentration of the reactant. That's just a notation you're gonna have to be used to. So in general, Le Chatelier's principle, when you change something in the system, the equilibrium will shift to counteract that change. So if I added more of A, it's gonna want to kind of oppose that, as if, you know, it's rebelling against me increasing the concentration of A, right? So how would the system try to reduce the amount of A? Well, they could just convert it to B, right? If I added A, it's gonna want to decrease A again and go back to its original state by converting it to B. So that means there will be more of the forward reaction and there will be more of the products being formed. So we say that when we increase the concentration of the reactants, we shift the equilibrium to the right because it tries to counteract me adding in more A and try and convert it to B. That's kind of like the main theme with Le Chatelier's. I could be changing the system by increasing the amount of reactants, products, could be increasing pressure, temperature, but the system will try and counteract what I'm doing to it so that it tries to go back to its original state. Yeah, here's kind of like a worded summary. So if you increase a reactant, a concentration of reactants, the equilibrium will shift to the right. And this leads to more product being formed so that more of the extra reactant is used up. So you want to use up that extra reactant. The opposite effect will occur if the concentration is decreased. So we could also increase the concentration of the product, right? Again, same principle. It's going to want to counteract me adding on more of the B. So how does it decrease the amount of B? Well, we could just convert it back to A, right? So then we reduce the amount of B again. So it's going to favor the backward reaction and shift the equilibrium to the left. So increase in concentration of product will shift it to the left. Yeah, we'll get back to catalyst later, so don't worry about it too much. So next is, okay, so this is just a summary. The increase in reactant, then you have more on the left, so it's going to try and want to go to the right. So the equilibrium shifts to the right. If you increase the amount of products or the concentration of products more, then it's going to try and go to the left. That's a nice way to remember it. So yeah. Okay. That's the summary. We'll go over it again at the end again, so don't worry about it. Okay, so next is the second one, pressure. So pressure, I don't know how everyone else imagines pressure. I quite like to imagine pressure as, you know, just like these molecules just hitting the walls and applying a force. That's pressure. And obviously the more molecules you have, the more, you know, pressure there will be. So this is going to be the key thing to remember. More molecules then more higher pressure there will be. So how does that help us? Okay, so in this really simple diagram, right? Which side has more molecules? Well, we can see that obviously the right side has more molecules, right? There's 4. And on the left, there are 3. So the right side, if I keep on making more and more products, it's going to increase the pressure, right? Because there's more pressure on the right side. There's more molecules. So if we increase the pressure, sorry, examples. Okay, so, okay, it's a bit hard to see in this one because you don't see the chemical reaction. But let's say that this is with 3 molecules and 4 molecules on the right. And if we increase the pressure, right? I'm trying to increase the pressure. And we said that Le Chatelier's principle sort of counteracts whatever change I do, right? So it's going to want to try and decrease the pressure. And a way to decrease pressure is to decrease the number of molecules. So in this example, if we were to just take, these numbers literally, then it's going to want to go to the left where there's less molecules, right? So ignore the fat arrow here. It would favor the backward reaction to try and decrease the pressure because there's less molecules on the left side. So yeah, increasing pressure when we shift to side with the fewest moles, the fewest number of molecules. We'll go through this with a specific example. And if we decrease the pressure, we get this opposite effect where it's going to try and move to the side with larger number of molecules. Sorry about this slide. I don't think this slide is accurate. So, okay, so it goes to the side with most number of moles. So yeah, sorry, ignore that. Okay, so this is kind of like more of an example that you're going to see in exams. So obviously, they're not going to give you a diagram with, where you can count the number of molecules like that. They'll give you a chemical equation, right? And a way to see which side has more number of moles, is that you just add up the coefficient. So this is 1 N2O4 molecule. That's 1 molecule on the left side. On the right, we have 2 NO2. That's 2 molecules. So we see that there's a larger number of molecules on this right side. Not quite sure why that's stuck like that, but there's 2 molecules on the right and 1 molecule on the left. So, okay, if we increase the pressure, it's going to want to decrease the pressure by going to the side with less number of molecules. And the less number of molecules in this example is the left side because there's only 1 in contrast to 2 on the right. It's going to favor the backward reaction when we increase the pressure. And we decrease the pressure, it's going to try to increase the pressure by increasing the number of molecules, which in this case is on the right. Yeah, we'll get some practice on that at the end as well. Okay, so final one that you need to know is temperature. So you're going to have to just remember what endothermic and exothermic is. I am kind of have like an image of how I remember endothermic and exothermic. The endothermic, I imagine as the molecules kind of soaking up the heat energy, whereas exothermic, you're sort of like just releasing energy, releasing thermal energy. So if we increase the temperature, right? If we increase the temperature, we're kind of adding in this thermal energy, right? And as I said, the Chatelier's principle basically says that the equilibrium will shift to counteract whatever I'm doing to the system. So if I'm increasing the amount of energy in this, thermal energy in there, the molecules are going to want to soak it back up, right? So just soak up that thermal energy that's in excess. So in that case, it's going to favor the endothermic reaction. So here it's going from right to left, but remember that it's going to depend on which reaction you're doing. So that's something you're going to have to look out for. In this particular example, the endothermic reaction is backwards. So yeah, increase in temperature, then the molecules are going to want to soak up that thermal energy. It's going to go favor the endothermic reaction. Yeah, increase in temperature, shift to endothermic reaction. And we'll go through this with the questions later. Okay, decrease in temperature, it's the other way around, right? So it's getting, it's getting colder, right? You're going to want to sort of heat the room back up again if you're decreasing the temperature. And if you want to heat back the room, then you're going to want to burn something, right? And burning is an exothermic reaction. You're going to want to go from, you're going to want to favor the exothermic reaction. And in this case, exothermic is forward. It's going to shift the equilibrium to the right side. Yeah. And just a key thing to remember is that they're not going to tell you which side is exothermic and endothermic, right? That would make it too easy. So what they'll tell you is they'll give you the enthalpy change. And you have to remember that the negative enthalpy change means exothermic, and a positive enthalpy change is endothermic. You're going to have to remember that. So if they give you that the forward reaction is positive enthalpy change, that means that the forward reaction is endothermic. And if the forward reaction is endothermic, then the backward reaction is going to be exothermic, because it's going to be, opposites. That's kind of speed it through that, because I want to make some time for some questions. Okay, so next. Okay, so we have an example here. Okay. So before we move on to catalyst, we'll do an example with this one. So this is kind of like how they will give it to you in exam, right? They'll tell you that delta H, so the enthalpy change of the reaction, is negative 82 kilojoules per mole. And the number is not too important. The important bit is that it's a negative. So they'll always give you the enthalpy change for the forward reaction. So this is saying that the forward reaction is exothermic. That means that the backward reaction is going to be endothermic. So if we increase the temperature, we want to cool down the room again, right? It's getting hot, and then you want to cool it down because Le Chatelier's principle says that it counteracts whatever change I make to the system. If I raise the temperature, then the equilibrium will shift to try and lower that temperature. They want to soak up that thermal energy, and that's endothermic, right? So endothermic in this case is a backward reaction because the forward reaction is exothermic. That means that the equilibrium will shift to the left if we increase the temperature. So next we can move on to catalyst. I think there were some people talking in the chat. Yeah, it's exactly right. So I like to imagine like the catalyst, like when you watch YouTube videos and you've got the double speed button, right? Which you will do a lot when you start watching lectures at university. You'll hit the double speed button a lot. But essentially, that's what a catalyst does. It just speeds up everything. It speeds up the forward reaction, the backward reaction, and how quickly the equilibrium is reached. It just speeds up everything. But it does not change the position of equilibrium. That's extremely important to remember. Adding a catalyst to a reaction has no effect on the position of equilibrium. It speeds up the forward and backward reaction by the same amount. So I just remember catalyst, double speed. It's not technically double, but it's good to kind of have like an image to help you remember. It just speeds up everything. And yeah, the other thing you need to know is that it speeds up the rate at which a reaction reaches dynamic equilibrium. Because if you recall from the beginning when we were explaining with the A and B, at the very beginning, right, you just have the reactant and you haven't reached dynamic equilibrium yet. You just have the reactants and none of the products. And as time goes on, more of A gets converted to B, and then eventually you get a dynamic equilibrium. But it takes time to get to that dynamic equilibrium. And adding a catalyst can help achieve that dynamic equilibrium quicker. And the yield is not affected. Okay, so yeah, you just increasing both. So, okay, so we talked about kind of like the ideal way to, shift equilibrium from left to right, depending on the reaction. If you use the Chatelier's principle, you'll know exactly whether you want high pressure or low pressure, high temperature or low temperature to, get the most out of a reaction. But you can't always do that in reality because, for example, let's say Le Chatelier's principle predicted for you that you want high temperatures and high pressures to maximize, to shift the equilibrium to the right, where you have the most number of products being produced. But that could be impractical, right? Because high temperature and high pressures is quite expensive to kind of maintain that. And you might actually be losing money. That's kind of the other topic that you need to know, which is to know about the compromise in industrial processes. So the Haber process is just nitrogen and hydrogen going to ammonia. And it's an exothermic reaction forwards because remember, negative sign. So let's just think about temperature. If it's exothermic and you want to get the most amount of ammonia, you want to shift the equilibrium to the right in the exothermic reaction. That means that we want to lower the temperature because that's the opposite, right? Exothermic, I imagine it like, burning wood, right? Burning something is exothermic. That raises the room temperature of the room. You want to do the opposite of that. So lowering temperature would be the way to get the maximum yield. In regards to pressure, there are one nitrogen molecule, there's one nitrogen molecule and 3 hydrogen molecules, right? That's 4 molecules on the left and then 2 ammonia on the right. We have more molecules on the left and less molecules on the right. So the right side has lower pressure because there's less molecules. Yeah, so the right side has less number of molecules. So that's less pressure, right? Then we want to do the opposite of that. We want higher pressures. Just making sure, right? Higher pressures to maximize yield and shift the equilibrium to the right as much as possible. So we want lower temperatures and higher pressure. This is what Le Chatelier's principle says is the best. But there's some issues of this, right? So first of all, low temperature, it will shift the equilibrium to the right, but there's a problem with that because at lower temperatures, as you might already know, you get lower rate of reaction. So even if we had a higher percentage yield, we're just gonna have a slower rate of reaction. So that might not be practical. So we need a compromise. So we need a higher temperature of around 400 to 450 degrees. And this ensures that we still get a reasonable amount and we're not, slowing down the reaction too much. Just to summarize, the Chatelier's principle says, if you want to shift the reaction to the right, then you want lower temperatures and higher pressures, but low temperature is not so good for, considering the rate of the reaction. And also high pressure is actually very expensive to maintain for a lot of reasons. You obviously need extremely strong pipes because under high pressure, you get a lot of damage to even normally strong pipes would just break straight away. And hence a compromise of 200 atmospheres use. Even that's quite high, right? So you can imagine what a very high pressure is kind of talking about. It's much larger than 200 atmosphere, which is already quite large. You can imagine how much that would cost. So that's another thing. Yeah. In summary, a temperature of 400 to 450 degrees is used to give a high rate. So we're prioritizing the rate of reaction. Oh, yeah, exactly. So we use temperature that's it's not the temperature you think of when you hear a low temperature, right? 400 to 450 degrees. But we need that because it ensures that the reaction occurs at a high enough rate. where you can actually, get something. And pressure is not, it's high, but it's lowered from the ideal pressure, just because, high pressure is incredibly cost inefficient. So this is kind of like a table. So you're always going to get asked about temperature and pressure. If you want to increase maximize rate, you always would just want to kind of go all out with temperature and pressure, right? High temperature, high pressure, that's always going to get you the maximum rate, maximum yield. In this particular case, from the Chatelier's principle, we know that it's low temperature and high pressure. But this is only for the Haber process. Maximizing rate is going to be the same for any reaction, but to look at the conditions for maximizing yield, you're going to have to apply the Chatelier's principle to just make sure this is the right condition. And to minimize cost, you obviously want low temperature and low pressure. This is the case for pretty much any reaction, because it costs a lot of money to increase temperature, obviously, and increasing pressure as well. So I think the first row and the third row is actually quite easy to remember. Maximizing rate, you just want high temperature, high pressure. If you don't want to spend any money, you lower temperature and lower pressure. And to find the conditions for maximizing yield, you would use the Chatelier's principle. Okay. So let's do some questions, because kind of what you want to practice to get the marks in the exams. Let me just get out the questions. You'll find that a lot of the questions in exams are actually quite similar. So once you know how to do it, it's going to be free marks for you. Can people see my screen? Okay, great. Also, before we start the questions, does anyone have any questions? Just something you want just have clarified? So I did speed through that quite quickly. Okay, feel free to just like send questions in, clarification. Okay, what are the ideal conditions for Haber process, methanol, and ethanol production? Good question. I don't actually have that memorized. Well, we saw that one for Haber process a little bit. Don't know if I can find that straight away right now, because I do remember that was something you need to remember. So this is actually for the AQA syllabus, I believe. So AQA A-level chemistry, but it should apply. Maybe the mark scheme would differ slightly, but the reasoning should be the same. What characteristics do all reactions have at equilibrium? Well, if it's at equilibrium, then the defining property will be that the concentration of the reactants and products remain the same. Hence, it's called an equilibrium. Another thing to remember is that it's a dynamic equilibrium. And the reason we call it a dynamic equilibrium is because the forward reaction is still going and the backward reaction is still going. It's not like, just because the concentration of the reactants and products remain the same does not mean that the reaction is stopped. It's just occurring at the same rate, so it cancels out. That's the characteristics of all reactions at equilibrium. Yeah, and feel free to just keep sending it in. So ammonia reacts with oxygen in a reversible exothermic reaction as shown in the equation below. This is the first stage in the manufacture of nitric acid. Here we just get given the equation. And I guess in this equation question, they give you that it's an exothermic reaction. Just remember that, they could just give you a negative enthalpy. Negative enthalpy would mean exothermic. Just want to have that hammered in your brain, so then you don't forget, right? It could be quite nasty if you get it the other way around, because you'll lose all your marks. The negative exo, positive endo. The forward reaction is exothermic. Okay, state and explain the effect of an increase in pressure on the position of this equilibrium. Does anybody, do people want to like type in the chat what would happen? Would it shift to the left or the right? I'll just give you guys like 1 minute to type in the chat, left or right. Okay, I see a lot of people putting left. Okay, looks like there's no one putting right, so everyone putting left. And you're all correct. So it shifts to the left. And we can count, right? So we have got 4 ammonia and 5 oxygen. So that adds up to 9 molecules on the left. 4 molecules of nitrogen oxide and 6 water molecules. That's 10 total. We've got 9 on the left and 10 on the right. So there's less molecules on the left. That's good. The equilibrium shifts to the left, and because there's more gas molecule on the right. Yeah, I think there's a lot of people with different. Okay, so someone's talking about endothermic reaction. So endothermic and exothermic, it's only relevant when we're changing the temperature, right? Because it's endothermal, exothermic, right? Therm is like talking about temperature. So it's not actually relevant for pressure, but good try. Yeah, that'll be more relevant if we were asking about increasing temperature, for example, which we'll do next. Yeah. Does anyone have any questions about this one? Guess not. Feel free to ask any questions, by the way. So, okay. Next. State and explain the effect of an increase in temperature on the position of the equilibrium. And now, because we're talking about temperature, now we have to think about exo and endo. So for pressure, we think about the number of molecules. And for exo, we think about, sorry, for temperature, we think about exo and endo. So, okay, yeah. Type in the answers in the chat. It will be better with the reasoning as well. Okay. Wait until there's a couple more. Wait a minute. Have you guys all done this before? Because you guys look like okay. At GCC, okay. I forgot they did it at GCSE. Okay. I guess it's good to revise. Good. Yeah, it looks like most people, I think everyone's actually put to the left. Yeah. So the forward reaction is exo and the backward reaction is endo. If we increase the temperature, we want to soak up that excess energy, right? So we want to go endo because that endothermic, you're soaking up energy, whereas exo, you're releasing energy. Think of like burning something, right? I would think of burning like wood for exothermic. So it raises the temperature. It's the opposite of this. And endo in this case is a backward reaction. So if we're doing the backward reaction more, then that means we're making more reactants and the equilibrium will shift to the left. Yeah. It's just like a general kind of marks. I know everyone's doing quite different syllabuses. Some doing IB, some doing did someone mention AP? Not quite sure, but generally this will get you the marks. So yeah, forward reaction is exo, and yeah, exactly, yeah. They don't generally get too creative with these kind of questions. So as long as you've got the mark scheme drilled down and make sure that you don't get it the wrong way around, you should be fine. I just added this in here because I think this question kind of tests a little bit, understanding of the terminology. The Haber process is a homogeneous dynamic equilibrium. What does that mean? Homogeneous dynamic equilibrium. So let's break it down. Does anyone want to put down what dynamic equilibrium means in the chat? I think it's quite important to homogeneous is same. Okay, but what's the same in this case, right? Want to be more specific. Okay. Good. Seeing some good answers. Okay. So yeah, I'm seeing a lot of good answers. So yeah, you guys are exactly right. So just break it down. So dynamic is dynamic because, well, what's the opposite of dynamic? Dynamic actually. Why is it dynamic? Do people know the opposite of dynamic? The specific term I'm looking for. It's not too important to know, but it will help with, other STEM subjects as well. Yeah, static. Static is what was before. You could have static equilibrium as well in other subjects. And a key difference is that in dynamic, the reaction are still going on, right? So and the equilibrium means that the concentration of the molecules, the reactants and products, they stay the same. But dynamic means that the reaction is still going. It's like still moving kind of thing. So just look at the mark scheme. And yeah, homogeneous, I think everyone got right. Homogeneous. The homogeneous means that they're all in the gas phase. Okay, so dynamic means that the reaction are occurring in both directions. And equilibrium just means that there's a constant concentration of reactants and products. Okay. Good. You guys are doing very well, actually. I'm quite impressed. Okay, so another question here. So a mixture of hydrogen iodide, hydrogen and iodine, all in the gaseous state, so it's homogeneous, establishes dynamic equilibrium if a constant temperature is maintained. Okay, so first off, what does this plus 9.6 mean? Oh, yeah, go back, yeah. I'll just go back for a moment, okay. Can I move forwards? Okay, all right. So yeah, I think everyone's put it. Endo, that's something you just want to get into the habit of doing. Whenever you see a reversible reaction and then you see like enthalpy, you just gotta go, is it exo or the endo? So yeah, it's endothermic. The forward reaction is endothermic. We can skip the first one because it's the same question. Second one, how, if at all, would the proportion of hydrogen iodide present at equilibrium change if the temperature were to be increased? What does everyone think about that one? So yeah, guys, I'll send you on the chat Actually, hold on. So I'll send the link to the YouTube channel. So in the meanwhile, type in the chat what you guys think the answer for 2 is. Right, I've put the link to the YouTube channel in the chat. People wanna. So we don't give out the slides itself, but we do put the videos on YouTube. So you can just watch those videos. Okay, so getting some answers now for question 2. Okay, starting to get some mixed answers a bit now. I think it does get tricky because so far we've been looking at examples where the forward reaction was exothermic and now it's suddenly endothermic, isn't it? So it's easy to get it the wrong way around. Which example? This is AQA, I believe. I think it's AQA. Yeah, I'm not 100% sure then. Okay, so some people saying, okay. This is a good question because some people are, it's quite like mixed, isn't it? So some people saying hydrogen iodide is increased and some people saying it's decreased. So let's go through it. So if temperature were to be increased, so we're kind of increasing the temperature of the room, right? The Chatelier's principle says that the system would, or the equilibrium will shift to counteract that change, right? You want the equilibrium will move to try and lower that temperature. So how would it lower the temperature? So it would, okay. So I'm just reading the chat. Yeah, it takes in heat. It tries to soak up that amount of thermal energy, right? And when I always think about it as soaking up and then endothermic. Right? Endo means like to go, it's like in, right? Going in. So you're soaking up that thermal energy, it's going in. So it favors that endothermic. And in this case, endothermic reaction is the forward reaction, right? So it's gonna favor the forward reaction. So more hydrogen iodide will react to form hydrogen and iodine. Equilibrium will shift to the right. And when it shifts to the right, we have less of the hydrogen iodide present. So the answer is that it will decrease. So I think there was quite a lot of mixed answers because it is a tricky question. So yeah, let's look at the mark scheme. Proportion of HI expected to become smaller because the reaction will respond to temperature increase by shifting in the endothermic reaction. So a good way to know if you're in the right line is I see that some people, more than one, have said that, you know, because it's exothermic, it will react, because it's endothermic, it will, sorry, because temperature is increased, reaction will shift to the right. But to the right is a bit too vague. You should say that it will favor the endothermic reaction, direction, or exothermic. That's the kind of that's how you would know your reasoning is along the right line. It shouldn't be to the right or to the left. You should be saying whether it's to the endothermic direction or the exothermic direction. In regards to pressure, then you'll be thinking about to the side with less number of moles or to the side with a larger number of moles. That's kind of how you want to just remember, this is how you want to learn it. because you don't want to accidentally remember the wrong thing. Okay, so I think last question is to do with catalyst. The reaction is catalyzed by metals such as gold and platinum. How, if at all, would the proportion, oops, no one saw the answer, right? How, if at all, would the proportion of hydrogen iodide present at equilibrium change if the reaction were to be catalyzed? Justify your answer. Okay. Do people want to just put that in the chat, what they think is the answer? Yeah, good. I think everyone has written the same thing. Well, it's just the buildup of these things, right? So you just want to increase the number of subtopics that you're good at, and then that eventually. Yeah, everyone has their strong topics and weak topics, so you kind of want to just start off by, making one topic really good, and then you can kind of sort of expand that. So when I did exams, I would always just flick through the exam paper and just, if I saw, like, for example, an equilibrium question, right, then I'd be like, oh, that's 3 marks, and I just start with that. Or there were other topics that I was good at, and then I would just start with that. And it just means it's just guaranteed marks, right? These topics do come up quite a lot, and it's 3 marks. So just want to try and increase the number of free marks that you can get, because there's more than this topic that's always like, a similar format. But yeah, let's move on. So no change expected because catalysts affect only the rate at which equilibrium is attained. I think most people had basically the same exact wording. One thing I would say is that make sure you answer the question the way that it's asked. The question is asking about essentially, would the proportion of the hydrogen iodide change? So in your answer, you should definitely say that the proportion of hydrogen iodide will not change. You can't just say that the rate, it only affects the rate. But I know people would just put that because it's just a chat, but just something to be careful about in exams. Be precise in how you answer your question. Okay, so that's the questions I had on my side. I'll try and get, I think we have time for a couple more questions, so we just get up. We started a little bit late, so let me get another question out. So, give me a moment. Let me just find the right question. Okay, we can do this one as well. We can skip part 1. People can see my screen, right? So you can skip this displayed formula part. So decide whether high or low temperature and pressure would give a higher proportion of cyclohexene at equilibrium. Justify your choice in each case. So here's the equation. Let me see if I can do it. Just put it in the chat if you guys have an answer. Oh, is it quite hard to see? Sorry, hold on. Give me a moment. I'll just move it a bit so you can see it. This is the last question, by the way, so I'll just quickly move it to PowerPoint, so then you guys can see it better. Okay. Okay. I think you guys can see it a bit better now. The cyclohexene is, yeah, C6H10. And decide whether higher or low temperature and pressure would give a higher proportion of cyclohexene at equilibrium. So low temperature as, okay, sorry, I'm just reading out everyone's answers. So, yeah, and the forward reaction is exothermic. We'll start going through it because we don't have that much time left. So yeah, I think everyone has generally the right idea. So that forward reaction is exothermic. So if you want more cyclohexene and you want to shift it to the exothermic side, then you want to lower the temperature, because when you lower the temperature, the equilibrium will shift to try and counteract that change. It's going to try and increase the amount of heat. And we said exo, burning wood, right? Burning wood is exothermic, so it heats up the room. So pressure, so that's low temperature. And for pressure, we have 2 molecules on the left and 1 molecule on the right. And if we want to shift it to the side on the right with a few number of molecules, we want to increase the pressure. Because when we increase the pressure, the equilibrium will shift to the side with less number of molecules, because less number of molecules means less pressure. So yeah, high pressure and low temperature. That's kind of like the end. Does anyone have any questions regarding this topic? That's good to hear. Yeah, just give people, that's basically it. Give people like an extra minute or two to just ask anything, about this topic if you want. Is this from Cognito? What's Cognito? I'm not quite sure what Cognito is, but let me look it up. Oh, do you want the answers for this question? Sorry. There was low temperature and high pressure. I'll show the mark scheme as well. I think this was, let's check which question it was. Question 13. So I'll try and get that up as quickly as possible because the meeting will end soon. Question 13. Okay. I'll put the answers up in 10 seconds. Okay. There we go. So this one. Okay. Yeah. Is that all right? Are you able to give us the questions for future practice? The questions we went through today, the question we went through today, it's gonna be on YouTube. I think I sent the link earlier. I'll send it again to the channel. The link to the channel. And it's not, and I think it'll be up there sometime. So then you can check the question that we went through today. Oh, whoops. I think I accidentally sent it by DMs. I'll send it to everyone. Yeah. So that's the link to the channel if anyone wants to check out, you know, today's meeting and any of the previous meetings as well. Yeah, that's it. Question about Casey. Yeah, I think Casey will be good question. It wouldn't be for liquids, no, because you wouldn't be able to have a concentration for liquids. But yeah, it's just aqueous and gaseous. So I'm just responding to a question in DMs, but yeah, you're absolutely right. It's only for gaseous and aqueous. Yeah, I'm gonna stop the meeting here. Thank you everyone for attending and have a nice evening. Bye.